All right, this is going to be video 5 for the topology of the reals, I guess, series that's part of the YouTube playlist of the baby reel analysis. So the last video was a video on a proof about neighborhoods being open sets. And in this video, I'm going to go over what limit points are and closed sets. So we're going to have a metric space. So let's say X comma D. These are metric, X is the set. So this is going to be a metric space, so MS. And we're going to use a point in that space, so P and X. And then E is going to be a subset of X. And first, we'll go over limit point. So P is a limit point of E if for all R bigger than 0, the punctured neighborhood, so I'll first write it in shorthand and then I'll elaborate on this notation. So this is going to be in subscript R, it's got an asterisk here. That asterisk is going to indicate that this neighborhood's a punctured neighborhood. So for all R bigger than 0, the punctured neighborhood intersect E is non-empty. All right, so every punctured neighborhood of P always contains elements of E. So I'm just going to go ahead and write that. Every punctured neighborhood of E, every punctured neighborhood of the point P always contains at least one element from E. Okay, so recall what a neighborhood is. So this notation in RP is going to be the set of Q such that the distance between P and Q is less than R. And so like as a picture, you can think of it as a ball. So we got a ball centered at P. And I'm not including the boundary of the ball. And it's got some radius R, and then Q is just some point that's lies within that open ball or neighborhood. So this is my shorthand for neighborhood in BHD. So this is just a neighborhood of P. A puncture neighborhood of P is basically the same thing, but we just take the point P out of the set. So imagine the center point now is an open dot, not including P. All right, that's a punctured neighborhood. And the notation is going to be this. And so it's the same notation for neighborhood. It's just got an asterisk over that. And so that's going to be the neighborhood of P taken out the point P. All right, so this is what I mean by punctured neighborhood. So everything in this ball, but without considering point P itself. All right, so that's what it means to be a limit point. Now let's consider a set E. I guess first, let me do a neighborhood, puncture neighborhood in R. So what does this look like in the reals with the standard metric, Euclidean metric? And so I usually use DE for that, for Euclidean. Well, that's just going to be an open interval, but with the center point of that open interval taken out. So we're going to have, so let's say this is the real line. We're going to take out the center, and this will be my interval. And so we have the center point taken out, P, and then it's got the endpoints that are a radius distance from P. So this will be P plus R. and then the left endpoint is P minus R. All right, so that's a punctured neighborhood and the reals with the Euclidean metric. All right, so limit point. So P is a limit point of a set E if every punctured neighborhood of P contains at least one element of E. So I'm going to draw a picture to represent what that means, like the set E, and then P being a limit point of that set E. This is just a picture of a punctured neighborhood versus a regular neighborhood. All right, so consider this our set E. Again, this is sort of abstract. We don't necessarily know the metrics. What the metric space is, it's just some metric space with X, comma, D. And then E is going to be a subset of X. So I drew this as my set E. And you see I have dash marks here and then solid right here. Now the solid is including the boundary. And then I also have this point over here. That's part of E. And the question is, what are the limit points? All right, well, any interior point is a limit point because let's say I pick this as my point, and let's take, again, we're going to consider puncture neighborhoods. So imagine that at this point, that's an interior point. I can draw a ball around it for any radius with the center point not considered, and still will lie within E. So this point, imagine the first, it's a point in E, and then I take it out, so it becomes an open dot, like that. Imagine that's what it is here. And that ball or neighborhood lies within the set E. All right, so any interior point is a limit point. All right, that doesn't really surprise us. Now I can get as close as I want to the edge of E here, and I can always find a ball that's small enough um, that's still contained within the set. And so I could have a limit point really, really close to here, but we're not including the boundary, so it's still in the interior. Now, what happens when I get to the boundary? So this area of E, we're including the boundary, whereas up here we're not. So I can also be part of the boundary. So if I'm part of the boundary, I can still draw a neighborhood or a ball around the point. Now imagine I take that point out. I'm not considering it anymore. So choose a point on the boundary, then take it out. Where that area is, I can still draw a ball around it, and it still contains at least some element from E. In particular, it would be on this side of the ball. Whereas this side of the ball or neighborhood, it's containing elements of just the set X that are not in E. So on the boundary itself, those are limit points as well. So even here, this punctured, you can do a punctured neighborhood around P, and it will always intersect E. So it's non-empty. And this particular P is part of the boundary of E. So I say P element of boundary. And then whereas I could draw a neighborhood or a ball around P as close as I want to here, but this boundary is not included. So I can always get a ball that's entirely contained in E. And then any interior point, because this is an interior point as well, but every interior point, I can always draw a ball and it's going to intersect E. In fact, it'll be contained entirely in E. Now the question is, what about something like this point that's like floating off into space here? So this is still part of E. Now that's not a limit point. So this is not a limit point. So let me erase this right here. So why is that not a limit point? Is because if I take the point out, I draw a puncture neighborhood. Imagine now it's an open dot, and then I draw a neighborhood around it. Then none of these members of this set are part of E. No matter how small I make the radius. Again, we don't include the center point. It's a punctured neighborhood. But this point itself, if I draw a punctured neighborhood, no matter what size of R, it's going to always not intersect E. And so because it's never intersecting E, it's going to not be a limit point. Now, Rudin gives the term isolated points. So if P's and E is not a limit point, of E, then uh, P is considered an isolated point. In particular, you could think of it as P's and E, and then the puncture neighborhood around that point intersecting E is the empty set. Okay, because we're not including the center point P, so it's a puncture neighborhood. In fact, if we don't include it as if we include the center point, so it's just a regular neighborhood, not a puncture neighborhood, and we intersect E with that, it's just that center point P. All right, so this is an isolated point. No matter what neighborhood I draw or ball I draw around it, it's going to never contain elements of E if I don't consider the center point. Now, it should be stated that a limit point does not have to be part of a set. Have to be part of E. Right? Because, like, for instance, if I consider a point that's on this boundary, but the boundary's not included in E, then I can always draw a ball around it, and it still, on this portion, will contain elements of E. But this point itself is not included in E. And so this would be a case where the limit point is not part of the set E. Whereas if I'm on the boundary, where it's the boundaries included, then I do have the limit point in the set. So a limit point does not have to be part of E itself. And that brings me to the next definition, which is the closed set. So a set is closed if it contains all its limit points. So imagine this is my set E, and I including the boundary. So all limit points of this set, which I can have an interior point, and that's going to be entirely contained in the set. Again, puncture neighborhood here. Now, if I choose a point on the boundary and to do a puncture neighborhood, so I say this point originally is on the boundary, now take it out, no matter what ball I draw around it, it's still going to contain elements of E that are on this side. So it's a fancy way of saying that a set is closed if it contains its boundary. So contains its boundary. All right, that's just a sort of how I think of it. Is it contained its boundary, so the whole boundary shaded or solid, whereas this one we don't have the boundary up here, and so these points that are on this dashed line that are not actually an E, those are limit points that are not an E. So this would mean the E is not closed, because it doesn't contain all its limit points. Whereas with this one, the boundary is included, and so that means the set is closed. All right, so that's the definition of closed. Now, so like in R, again, with the Euclidean metric, any closed interval, so this is A, B, so this is the closed set. All right, of course, we can have any point inside of the interval. Let's say we choose P in here, then draw a puncture neighborhood around it. And that's just this open interval. It's going to be contained inside of the closed interval AB. So these interior points are part of the closed interval AB. And then I can choose B to be my, let's say B is a limit point, because again, I draw a punctured neighborhood where I take the point out, and any interval I draw around it, no matter how small, this left side is going to have elements that are part of the closed interval AB. So this is a closed set. All right, so here's a definition, which is called the closure. So we use this notation, E with the line over it. Again, I'm using Rudin's text, and this is going to be the closure of E. So the closure of a set is defined to be the set union with E prime. And E prime is going to be the set of limit points of E. All right, so that's the closure of a set. It's the set union with its limit points. So consider, again, now I'm going to consider it an abstract metric space. And I drew like the little blob kind of thing. So let's say I have this and this point. And let's say that's my point E. What are the limit points of E? So what is E prime? Well, E prime is a set of limit points. This is an isolated point, so this is not a limit point. So that would not be part of E prime. We have the boundary here. These are going to be limit points. Any point I pick on the boundary, draw a ball, it's going to intersect E. And then we have this portion of E that's not including the boundary, but those are also limit points. And then we also have the interior points. So E prime basically be this blob, but enclosing this boundary. So it would, it isn't gonna be like identical, but you get the idea. So it's basically the same shape as this, but including this boundary area. This is E prime. So the closure of it would be this set unioned with this set. All right, so E, the closure of E would be this set E all of this, including this isolated point, unioned with this set that's the limit point to E. And this is just an abstract picture representing the concept. So let's do a concrete example. Let's say we use the reals again, Euclidean metric. And let's say my set E is the interval with the open interval 0 to 1 with the closed with a bracket union 2. And I want to figure out what's E prime, and then what does the closure of E look like? Okay, so let's say this is 0, 1. That's definitely not drawn to scale, but you get the idea. 2. So first, let's just draw E. So E is going to be everything shaded in between 0 and 1. And then I'm not including 0 in E, so this is be a open dot or a parentheses. And then at 1, I'm including it. So that'd be a closed dot or a bracket. And then at 2, I'm including it. So this is E. Now, what is E prime? Well, you're going to have everything between 0 and 1 is a limit point, because that's in the interior. 0 is also a limit point, though, because at 0, I can draw a ball around it. It's going to spill over to the right side and have some elements of E. So we're going to include 0, and then all of this stuff and 1. But the point 2 is not a limit point, because if I draw a punctured neighborhood, so take it out, and any ball I draw around it is still going to be, there's a ball that I can draw around it that's not intersecting E. So that's the negation of the meaning of limit point. So around 2 itself, there exists a radius so that the punctured neighborhood around 2, so let's say in punctured neighborhood, so take the point 2 out, and intersecting E is empty, is the empty set. Right, so like this would be like our punctured neighborhood, and let's say I use R equals a half. The left endpoint of that would be 1.5, 1.5, and then the right endpoint of that would be 2.5. And then everything in this is not an E. And again, I do a puncture neighborhood, so I'm not including the point 2 itself. It's just a fancy way of saying that the point 2 is itself an isolated point. So that would not be an E prime. So in conclusion, E prime would just be the interval 0 to 1 with closed brackets. So basically everything in E, but besides point 2 is not in E prime, and then I include 0. So the closure of E is E union E prime. Well, that's going to be E is 0 to 1, union with the point 2. All right, so that's E. Union with E prime, which is 0 to 1 with brackets. And so that's going to be 0 to 1 with the brackets, union 2. That would be all of this. and 2. All right, so that's a concrete example of the closure of a set, defining the closure of a set, and also defining the limit points of that set. So I think that's where I'll end this video. And in the next video, I'm going to do an example. And the example is going to be prove E prime is closed and prove that E and E bar, or the closure of E, have the same limit points. And then answer a question that's on, do E and E prime always have the same limit points? And that's that's what I'm going to do the next video. So this video introduced the concept of closed, um, concept of limit points. So a set is closed if it contains all its limit points. I guess before I end it, there's a alternative definition for closed. So we say E is closed if E complement is open. So a set is closed if its complement is open. All right, I did not state that earlier. I should have stated that. So E complement, this would be all the elements of X such that X is part of X taken out E. So it's subtract out E from X. As a rough picture, see, this is my area that's going to be X, and then I have, let's say I include the boundary for E here. So imagine this is E. So it's a closed set, meaning because it includes its boundary. So all the limit points are part of E. Now what's the complement of E? The complement of E, basically the same shape, but I use dash. So imagine I have this shape and now I take out the boundary, and then it's going to be everything outside of E. So all of this would be E complement. And so this is open because it doesn't include, the boundary is not part of so like every point's an interior point of E complement. So get a point here, and an interior point means there exists a radius such that that neighborhood's entirely contained in that set. So if I pick a point out here, I can find a ball around it, and that ball is going to be contained in E complement. And then I can get as close as I want to here. Imagine I can zoom in and I could find a radius small enough such that that ball or neighborhood still contained in E complement. All right, so that's also a useful definition. A set is closed if its complement is open. Sometimes it might be difficult to prove a set being closed using the limit point definition, and it might be easier to prove it based on the complement being open. All right, so that's where I'll end it. In the next video, I'll do this problem.